Our third counting technique is known as permutations. Permutations, which is represented as NPR, they are the number of ways you can order R objects out of a set of N total objects. This is how you can do a computation of a permutation, which we will get to shortly. But first, what does this mean? Well, in the previous slide, we talked about, for example, 10 factorial meant the number of ways you could order 10 different objects. But let's say you weren't interested in all 10 positions. Maybe you're going to order 10 objects, but you're only interested in the first 3 positions. That then would be 10p3 that you would want to compute. We can do this computation using this formula here. And n in this case is 10, r in this case is 3. So the numerator would be 10 factorial divided by n minus r factorial. N minus r is 7, so we'd have 7 factorial in the denominator. And if you wanted to do this computation by hand, you've got 10 factorials, 10 times 9 times 8 times 7 times 6 times 4, all the way down to 1. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And we wouldn't want to multiply the numerator and denominator first. We'd want to divide out common factors, and these factors divide evenly into these here, leaving us with 10 times 9 times 8, which is 720. We will get to see an example shortly to see how and why this is very valuable. But a couple of things you first need to note. One, in this computation, it is possible to get 0 factorial. 0 factorial is defined specifically as 1. Just take that for granted. It makes our mathematical system complete. Also, notice that with permutations, the order matters and you cannot repeat, just like with factorials. Our fourth and final counting technique is known as combinations. Combinations, which is read n choose r or NCR, represents the number of ways you can choose R objects out of a set of N total objects. Now, this may sound very similar to the previous one. However, the big difference here is you're choosing R objects out of a set of N total objects, and the order does not matter. So with NCR or N choose R, the order does not matter. You also cannot repeat the items. Here is the formula for how to compute NCR. So for example, in previous one, we did 10p3 was equal to 720. If you wanted 10 choose 3, which the major difference here is that the order does not matter in this one, whereas order mattered in this computation. And we're going to get to examples shortly so you can see exactly when you would want to apply each one of these. So 10 choose 3 is n is 10, so you get 10 factorial over 3 factorial times the quantity 10 minus 3 factorial, which is 10 factorial over 3 factorial times 7 factorial. So the difference here is you now have this 3 factorial in the computation that you didn't have when we did this computation. That 3 factorial is ultimately cutting out the repetition that you would get when you consider order mattering. You end up with, we already saw that this divided by this is 720. And 3 factorial, of course, is 3 times 2 times 1, which is 6. Divide those, and you get 120. Let's summarize the 4 counting techniques that you should know, and then we'll get into some examples where we have to decide which counting technique to use, and you'll see sometimes you'll be able to apply more than one. Here is our summary. With the fundamental counting principle, order matters and you can repeat objects. With factorials, the order matters and you cannot repeat objects. With permutations, similar to factorials, order matters and you cannot repeat objects. With combinations, the order does not matter and you cannot repeat objects. Now, these aren't all the possible combinations of order mattering and whether it can repeat or not, but these are the 4 that you need to be concerned with in this class. Let's take a look at a few examples. Here we revisit one of the problems earlier used to discuss some of the key components of counting. Problem 1 says 7 people enter a race. The person who finishes first receives a gold medal, the second gets silver, and the third gets bronze. How many ways can the medals be awarded? Again, it's highly recommended that you first ask yourself, does the order matter, and can I repeat or not? So does the order matter in this scenario? Well, of course, it's a race, and the first person gets gold, the second person gets silver, and the third gets bronze, which are three different types of metal. So order certainly matters here, and you cannot repeat. The person can't get first and second place. So order matters, and you cannot repeat. So we have a couple of options here. One of our options is using the fundamental counting technique, because with the fundamental counting technique, the order matters, but you can repeat, but it's not necessarily necessary that it does repeat. So let's first use the fundamental counting principle. So you've got the first position, which was go to the gold, second is silver, and third is bronze. When 7 people enter the race, there are any of the 7 could possibly finish in first place. Then once that person finishes, any of the 6 remaining could finish in second place. And then once those 2 positions complete, we could have any of the other remaining 5 could finish in third, giving us a total of 210. Since this is a scenario where the order matters and you cannot repeat, we also could use the permutation technique. So in this case, n is 7, R is 3 because there's only 3 positions that we're concerned with. So we could compute 7p3, which by the formula is 7 factorial over the difference of 7 and 3 factorial. So you get 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1 over 7 minus 3 is 4, and then 4 factorial is 4 times 3 times 2 times 1, leaving us with 7 times 6 times 5, which is 210. Exactly the same thing that we got over here. You will see that doing this computation by hand is not necessary. Every scientific calculator has a permutation function built in. I will show you how to find and use that in your own calculator. So notice that we were able to solve this problem using the fundamental counting technique and also using permutation technique. You do not need to solve the problem twice. You could do it either way. Let's take a look at problem 2, which we saw earlier. 7 people wait for a cab. The driver says he only has room for 3. How many different groups of 3 could possibly ride? Well, we already established that the order does not matter here. The 3 people are going. In the cab, it doesn't matter the order of the 3. And you also cannot repeat. You wouldn't have, say, Adam, one person take up all 3 seats. So you cannot repeat. Notice now, in this scenario, when you have the order does not matter and you cannot repeat, we actually only have one option, and it is the combinations technique. So we want to compute NCR. In this case, N is 7 because you got a total of 7 people, but the taxi driver can only take 3, so R is 3. So we want to compute 7 choose 3. Again, 7 choose 3 by the formula is 7 factorial over 3 factorial times 4 factorial. And if you do this computation, we get 7 factorial divided by 4 factorial is 7 times 6 times 5 over 3 factorial is 6. Of course, if we divided out the 6's here, we get 7 times 5 leaves us with 35. So there are 35 different groups of 3 that the cab driver could take out of the 7 people. Again, this computation is not necessary to do by hand. I will show you how to find this function in your scientific calculator. Here is a third example, but notice it is not the original problem 3. The original problem 3 actually required a different technique. With problem 3, originally it was you have 7 different types of donuts and you can choose 3 donuts. That is a scenario where you can repeat and the order does not matter, which requires an additional formula beyond the 4 counting techniques that you need to know for this class. So here is a new problem 3. A meal at ABC restaurant consists of an appetizer, an entree, a dessert, and a drink. There are 3 appetizers, 5 entrees, 2 desserts, and 6 drinks to choose from. How many different meals are possible? Well, in this case, technically, and this is a little subtle, the order actually matters. And the reason the order matters is because you need to make an appetizer choice, then you need to make an entree choice, Then you need to make a dessert choice, and then you also need to make a drink choice. So the three appetizers, they couldn't be shifted over and put in this position because they're not desserts. So technically the order matters in this scenario. And you also cannot repeat. There are all four different tasks. And notice I just used the word tasks to describe this. In a scenario like this, I would simply use the fundamental counting principle. So you've got three different choices for apps, five different choices for entrees, two different choices for desserts, six different choices for drink, leaving us with a total number of meals possible at 180.